Thank you, Matias. So first of all, I would like to thank the organizers. It's always a pleasure to be in Rio. So on my behalf and also on the behalf of my students, I think it was very nice to obtain financial support, especially in these times of crisis. And so that was really great. So what I want to talk today is about the algebroid extensions, and I want to explain a few things of them. In particular, I want to explain how they are, how they can be considered as actions up to homotopy, where essentially you have a Lie algebroid acting on another Lie algebroid up to homotopy. Okay. So that would be the first part of the talk, and the second part is try to give an idea of an integration procedure for such actions. Okay, so this is work in progress. I mean, we are fairly confident this works. Up to, I mean, there's always some small details to fix, but okay, it works. So let me recall what is a Lie algebroid. And since I think a few of you are familiar with Lie algebroids, I will start with this result of Weintraub that describes Lie algebroid structures in terms of differential graded algebra. So here, so the notation for omega of AM, the sections of the exterior algebra of A star. So I will talk about forms on A, okay? And so this says that a Lie algebroid is entirely determined by the complex that computes its cohomology, okay? And so here, what is the differential graded algebra? I mean, it's just an algebra with a grading and a differential. So it's since the forms already come with this wedge product, essentially once you fix your vector bundle AM over M, the only thing you're left up is to have some derivation of this algebra. Okay, so it's graded derivation. Okay, and what is important, is that, the main idea that you can think as forms on AM as some sort of generalized functions, and D as a derivation of this function. So it's pretty much like a vector field. So just to make one small point, where I think this result is really nice is, of course, this is functorial. So, for instance, if you want to describe a Lie algebroid morphism between two Lie algebroids, basically you can pass to cohomology and show that exactly what you have is a morphism of the DG algebra. Okay. Let me just. So, what is such a morphism? So say I want to describe a map from AM to AN. So this induces a map from AM, okay, to AM like this. So say I have a phi, I can put it back, okay. And so what you require is that phi star of alpha wedge beta would be phi star alpha wedge phi star beta, and well, D phi star is phi star composed with D. Okay, so what is it? I like this very much because, for instance, say you start with an application of I mean, a morphism of DGAs. Okay, so you have these two conditions satisfied. So this condition will tell you that it's a Lie algebroid morphism. Okay, and but what does this condition tell you? This condition tells you two things. It tells you that this map is the pullback of a map from here to here. Okay, and it tells you that it's smooth. Okay, So the reason I think this result beautiful is that here you just have an algebraic equation. It's completely algebraic. It's commuting with some product, so the algebra product. So the way I see things here is that, okay. So here you have algebra, basically, and here you have geometry, brackets, anchor, and so many times, you know, even for smoothness, there's a lot of things to check. But algebraically, it's just, okay, just checking this. So it's very powerful. It's a powerful way to write a lot of things in very short, okay, including the geometry, the differential setting, differential geometric setting. Okay. Okay. So let me talk a bit about the algebra, the actions. And from this point of view that I was explaining, because it becomes a leitmotif at some point, you just you see a algebroid, and okay, now I try to think of it in terms of DGA. So if you want to describe an action of a algebroid, maybe you should see it as a DGA, okay? And the idea is pretty simple, is that, say you have an action or a representation of a algebroid AM over either a vector bundle E over M, or submersion from a smooth space E to M, okay? So how would I obtain, how can I obtain some kind of a DGA? And the idea is just, if I have an action, say, I can take the semi-direct product, which is the so-called action algebroid. And the reason I'm happy with that is now this is a algebroid. Okay, so I can take forms on the action algebroids, and well, it comes with a DGA structure. Okay, so that's the way, the basic way we translate an action or a representation in terms of DGAs. Okay. Now, how do you recover the action? Okay, so of course there are conditions on the DGA. Where is it? On this. Okay, so there are some conditions on this DGA, but I will talk about it later on, okay? But essentially, how you recover the action, okay? So the forms on the semi-direct products are forms on A, tensor product with forms on E. So here, all the tensor products are taken over functions on M, okay? And essentially, what you do is that when you take the total differential here, and it's of the form alpha tensor F. There's the alpha tensor F plus alpha dF. So dF is just the Durham differential on E. And no, not even, sorry. So yeah, you have this derivation condition, okay, that is satisfied. And the d alpha, so this alpha here is a form on A. You recover the differential on A. And on the other side, you have some operator D of F, okay? What I mean is differentiating the F, you obtain this operator that goes from functions of E to functions of E omega 1 of M. I mean, I will make this clear, and I think there's a small mistake here, okay? But I will go back to this, okay? Okay, now let me, so that's about usual actions or representation. Let me talk about extensions. So what is an extension? So the definition is that an extension is just a algebroid morphism from AE to AM. So here I'm taking the algebroid morphism. I'm not imposing to have the same base. So AE is a algebroid over E. AM is a algebroid over M. One small comment on the notation. There's a pi, which is a vector bundle map, covering a pi. And as you can see, there is a small dot here. And it's just, it means, the dot means you take the map, the base map. So for an extension, what you do is just you take the algebroid morphism, and you impose that both pi and pi dot are surjective, meaning pi is surjective and it covers surjective submersion, pi dot on the base. Okay, so it's just you can think of it as a surjective algebraic morphism, as surjective as it can.
Yeah, it's not exactly the same as what Mackenzie called the vibration, the vibration.
Yes, I should look. The thing is, Mackenzie works a lot with over the same base, right? And yeah. So, I mean, part of this work, okay, yeah. I will give the example, okay. But Mackenzie does a lot of stuff, right? He does pullbacks, and of course, there are extensions over different bases. But the relevant part are really over the same base. And okay. So why is it called an extension? Well, for the simple reason that you can take the kernel of this map here, and as it turns out, it's a Lie algebroid. It injects into AE, and what you obtain is an exact sequence of Lie algebroid. Okay? So that's why they're called extension. And well, if you have an exact sequence, exact sequence, well, means surjective, right? So it's the same. I'm meaning that the kernel comes for free. So here are a few examples. The first basic example, of course, are Lie algebra extensions. You take an extension E of a Lie algebra G by K, which is the kernel. So it's just, you take a Lie algebroid morphism, you look at the kernel, and, well, you have an extension. Note that I'm not considering a central or abelian extension. I really want to have any extension. Another interesting example are Atiyah sequences. Say you have either a transitive Lie algebroid or a principal bundle. You can take a TP mod G, or just when TP mod G is transitively algebroid. You have surjective anchor, which is a Lie algebroid morphism. So, and the kernel is well known to be a bundle of Lie algebra, a locally trivial bundle of Lie algebra. Okay, so the first example are, those are all over a point, so those are all over the same base. This is a Lie algebroid over A, it's transitive, over M, sorry, so it's transitive. So the second example is over the same base. Now, if you want the most simple example over different bases, just take a submersion pi dot from E to M and take pi to be the differential. Now this is, you just have a surjective Lie algebroid morphism from the tangent of your total space to the tangent of your base. It should be an M, Tm instead of Tb. And what is the kernel in that case? It's what is usually called the vertical bundle. So that consists into vectors that are tangent to the fibers of the submersion. Okay. So let me make draw a picture. That I hope shall explain. So here, the thing is that, so here usually you have, maybe I should keep this in hand. So here you have a Lie algebroid AM, and say I'm going to take a point X, and you have your total space AE, and some surjective map as here. Okay, and as you can see, especially in the case of submersions, the kernel, okay, you can always, okay. So the kernel here is clear that it's a Lie algebroid over the fibers of the base map, this pi dot. Okay, so. In all the examples, if you want to have some kind of intuition, you should think of AM, the Lie algebroid, as being your base space, AE, which is the extension, is the total space, but the kernel really plays the role of the fiber. I mean, all the fiber all together. Okay? So in the case of submersion, what I mean by fiber is not just the fiber, but the tangent to the fiber. Okay? So the basic picture is that here you have K, okay, the kernel, which lies inside A, and you're projecting everything on AM. And of course, K is killed when you look on the base, so the base doesn't see the kernel. As it turns out, okay, there is indeed this kernel you can see as a family of Lie algebroid on the fibers. Okay, so it's always relevant to see this K, I mean, as the union of the restriction of this Lie algebroid to the fibers. Okay, and the restriction is always well defined. So I said the intuition is led by the last example here, but even for ATIA sequences, you can feel, I mean, you have this, you have a bundle of Lie algebras, and of course these are some kind of, they are the fibers of something, right? For the algebra extension, it's a bit more, sorry?
Can we just think about it like an algebroidization of the usual not vector, just locally trivial bundle exact sequence? Fibers.
Yeah, but right. So Right. The thing is, they are not really locally trivial, or it depends on how you define being locally trivial. You could say so. Yes, you could say so. Yeah. Right. Yeah. Yes. Even or like what is a it's subjective. I mean, even from differential point of view, what is a I mean, a submersion is right. Okay. So why do extension? So first of all, I'm going to explain that indeed extensions generalize actions for the following reason is that if you have an action or a representation of M on E, which is a vector bond or a submersion, so if you have such an action, you can form the semi-direct product. And as it turns out, this is indeed an extension of AM, the guy that is acting. Okay, so you should think as the base acting on the as the one being acting. That's what I mean. And but this one is very particular because if you look at the kernel, you see this map. The AM, the Lie algebroid structure is defined on the pullback by P of AM. So it's P star AM. So if you look at it projects naturally. I mean, fiber-wise, is the same as AM. So the kernel is just a trivial Lie algebroid on. It's a trivial Lie algebroid on the total space E, as it turns out. Okay, in fact, this condition that if you take if you take an extension and assume that the kernel is trivial, meaning that it's the trivial Lie algebroid over over E, that is the total space, then you have an action or a representation. Okay, so in that sense, extensions generalize actions. Okay, now I have to talk a little bit about harassment connections in that setting. So what is an harassment connection? So I'm choosing an extension AE over AM. So usually I'm just taking AE over AM and say here I have the kernel. Now somehow you want to split this sequence, okay? But because you're working with over different bases, what you can do is you take the pullback by the base map from E to M of AM. So that now you have an exact sequence of vector bundles over the same base, covering the identity, and you just take a splitting of this map, okay? And another way of saying it is that you basically split your total Lie algebroid AE as one part which is the kernel, which is vertical, and one part which would be the image of sigma here, and which is horizontal. Okay, so this is pretty much like a harassment connection where you split the tangent of E as a vertical and horizontal part. Okay. So now, once you fix such a splitting, such a connection, there are two objects that you obtain. One is a D, and the other is an omega. So what is D? D is a form on A, and it spit out a derivation of the kernel. Okay, and omega is a two form on A, and when you apply it to two guys in AM, it spit out a section of K. Okay, and the way they are defined is simply if you want to dA applied to, so this should be a derivation of K. So you take a section of K, and dA applied to some K would be just the bracket of sigma of A with K. So here I'm thinking of sigma of A, in fact, of a section of this pullback. I have this splitting. So now I can take the bracket in here. So here, as you can see, I'm using the bracket in AE in order to define this D. And this omega here, so applied to AB, which are sections of A, is just taking the bracket of sigma A, sigma B, and then subtracting the bracket of sigma AB. This one is the bracket of AE, and this is the bracket on AM. Okay, yes?
So, when the section is by an algebra, the second one vanishes, the omega vanishes, but D not necessarily vanishes.
Yes, yes, yes. So that would be what you call an action of, a usual action of AM on K. Yes, definitely.
But in general, it might not be nothing. No?
Yeah, yes. Right, right. But there are a case where D is essentially 0. I mean, and you still have an omega, right, for like central extension, this kind of thing. So for me, they come together. I mean, okay. So is there something? Okay, there are some structure. So I will usually refer to D as some covariant derivative or induced by the connection, and to omega as the curvature because, well, for obvious reason. In particular, I'm thinking of submersions. Okay. Now, so these two guys I cooked up using the bracket in AE. I'm hiding some conditions in all this equation, but they are not unrelated. Just take a couple d omega, you will not get an extension. But there are structural equations. One is that if you take, so that would be the curvature of D. So D, okay, dd, so here you have derivation of someone, so you can take the bracket of derivation and then subtract a d of, now if you have two sections of am, and you can take the bracket, so you make this difference. Now you can take the bracket of omega applied to two elements in here. This is a section of k, and so I can apply both sides here to a section of k, say. Okay, so just to make sure that this makes sense. So the first equation tells you that this map D has some kind of, has its own curvature that is related to the curvature of the connection. So essentially it says that the curvature of D is inner. Okay, so it's a bracket. Maybe it would be add as in the adjoint map with omega would be a better notation. Okay, so that's the first thing. And the second equation is that if you take the cyclic sum of dA applied to omega of BC, omega BC is section of K, dA is a derivation of K, so this makes sense. And probably the second equation, let me write them now. So omega, okay, dA is sigma of A, and omega is, well, up to sign, sigma. And so first is d minus d equals, I'm going to write it this way, add omega, so it's a bracket with omega. So this one I really want to write it as d omega. Okay. Okay, because this is a free form on A. This would be a free form on A with values in K. Okay. So probably the best way to write it down is like this. Okay. So now let me explain why representations are actions up to homotopy, and I don't really want to explain what is representation up to homotopy, so I assume that you know what it is. And if you don't know, I will kind of explain afterwards, like dropping some conditions.
Is that all the structure that appeared? I mean, you also have this like anchor map from.
Yes, I'm handing the anchor maps here. Yes, like like this D applied to. I mean, the symbol of D of A should project to the symbol of sharp of A. Okay, so I'm just trying to make it short because the fonts are too large. Okay, so why are representation actions up to homotopy as opposed to a representation up to homotopy? Is that in fact there is an equivalence of category between extension and structure of DGA module over omega of AM on omega of AM tensor omega of K. And so this is essentially language. Now we pretty much know what is an extension. Let me explain. I'm going to explain this part here. Okay. Okay, this is language, but it's definitely in the spirit of Weintraub, right? Saying, let's try to describe everything in terms of DGA module, and though that no representation up to homotopy will recognize. Okay, so what is a DGA module? So on omega AM tensor omega of K. So the definition is that first, it should be a DGA. So it should come with a differential. Okay? This differential I'm going to denote by d tot, and it goes from this tensor product to itself. Notice that I'm seeing this as somehow a vector field on these functions. Okay? So it comes with a differential. And the way it's written here, I already have a graded algebra structure because, I'm taking the tensor product of graded algebra. And so A tensor K beta, so A and B are forms on A, K and L are forms on, A alpha and beta are forms on AM, K and L are forms on K. And well, you just put the good sign, and hopefully the signs are correct. But okay. So what I'm saying is that for a DGA module, you want a differential, and you want also a graded algebra. But the graded algebra already comes for free. So I'm imposing that the underlying graded algebra structure is the one that I'm having already. Okay, so it's compatible in that sense. So I'm left with the differential, okay? And now there are some compatibility conditions, okay? And the compatibility condition is that the total differential, okay, of A. So if I multiply, so now I can multiply a form on A, a form K on the kernel by a form on the base. Just by this derivation property, okay? But what I'm imposing is that here, it would coincide with the differential on AM. Okay? So if you know representations up to homotopy, that's the condition that's appearing here. Okay? That's really the condition where you have a graded vector bundle, and you have a differential on this tensor product, and what you impose is a differential on the tensor product, and what you want is that this thing appear, okay, and this d dot. So that's really the condition. Okay? Note that implicitly I'm imposing that this d dot, of course, is going to be a DGA. Okay? Okay, that's so implicitly. Okay. So in the end, okay, let me. Okay. Oh, okay. No, then I will explain. Okay. Okay. So what's the idea of the proof? It's very simple proof in the end. It's just that, well, you choose a splitting. So once you have a splitting, you can split your total algebroid as a vertical, which is the kernel, and horizontal parts. Then you look at forms. Okay. So you have an isomorphism between forms on forms on your total algebroid. As lambda p over the pullback, okay, and tensor the lambda k of A star. So all this is very natural. And when you go to section, you end up with just forms on AM, tensor forms on AK. So here it's really a usual tensor product. This pullback somehow disappears because functions on E are absorbed somehow here. So, okay. So just I'm taking a splitting, and since on AE, remember that this is this is an extension. So this comes with a differential. On the space of on these forms, and I just transport the structure from here to here, and so the work is to check that. Okay, so this d dot as is transported from a DGA, so you have to check that the graded algebra is the same, and this d dot is just obtained by transport, and that you have this compatibility condition. Okay, but the compatibility condition, you see here, how do I multiply a guy in omega A with a guy in K? Essentially up to this isomorphism. So what I'm saying is that if you have alpha in omega of AM, okay, that somehow acts so here I did put it as a K, but say K that is in my module, omega of AM tensor omega of omega K, sorry, and how is this action? This is just like, so up to this isomorphism, is just taking the pullback of pi star of alpha wedge. Okay. Okay. And this compatibility condition here, which is the crucial one if you think in terms of representations up to homotopy. So this crucial condition essentially boils down to the fact that pi is a algebroid map, so it commutes with a differential. Okay. So, okay. So how does this? Okay, I want to pursue the relationship with representations now up to homotopy. Okay. So now your d dot now is on omega p of A. M tensor omega Q of K. So, and it has total degree. I should get rid of this, guys. This is my d dot omega of A M tensor omega of K. Okay, but here this is degraded. So what one can do is to decompose this differential into several degrees, just the way you would do for a representation up to homotopy. And so all these D appearing here, you can see them as forms on the base, now with values in derivation of omega of k of degree q. Okay. Now let me point out that those are derivation of the wedge bracket. So those differentiate. There should be a derivation in the sense of as algebra, graded algebra. Okay. And now comes the big surprise, and I prepared this slide for this, is that you're expecting that there's a lot of terms because of from representation up to homotopy, but no, in fact, the higher terms vanish. Well, I knew that since quite some time, but well, for me it was like a huge computation, but I will explain a little bit more.
These representations you are considering here are concentrated on positive degrees or negative degrees?
Well, it's omega of down, right? I mean, I'm taking a vector bond. Basically, I'm taking a vector bundle k over E, and I'm taking omega of k. So I'm, you know, it's concentrated in positive or negative depending on your. Okay. So yes. Of course, yeah. If there would be negative degrees.
So I suspect this is why you only have 3 terms.
No, but for instance, for representation up to homotopy, you know, even if it's concentrated in higher in positive degrees, you have an infinity of terms. It can be concentrated in degree 3, and you have a free form with values. No, degree 2, and you have a free form. But okay. But I will explain. Okay. So let me. Okay. So what I did is just translate extensions in terms of DGAs. Okay. And well, related with representation of homotopy, but it's just this process. Now let's go a little bit into the details. Okay. How does it relate with this this covariant derivative and this omega and all these things? Okay. Is that so when you look at the total differential, it decomposes in various degrees. And the first of them, which is degree, it augments the degree in the k in the kernel only, or formed in the kernel, is related to a differential on omega k, and it gives you the algebroid structure on the kernel. So I said, oh, whenever you take an extension, the kernel is a algebroid. Is subalgebroid. So essentially, the first term here gives you the algebroid structure on the kernel. Okay. The second terms, you see, it hires the degree of forms on the base, and keeps it gives you a derivation of degree 0. So it's obviously related with the covariant derivatives. In fact, it's essentially the dual of this operation. Okay. You pass to forms, and you extend to you pass to k forms on k. I mean, just what is induced on section. Okay, and now this d2 minus 1 is just the usual omega. Okay. Now what happens is that you see this d2 omega is a 2 form with values in degree minus 1 derivation. But what is a degree minus 1 derivation? It's exactly a section of k. So I'm taking the inner product. So essentially, this d2 minus 1 is the inner product with this curvature. So basically, if you try to dualize this, what you obtain is all these terms. Okay, and so there's no higher terms. This is because the derivation of forms on k vanishes for k inferior of minus 1. The reason is kind of, I mean, it's so simple, is that omega k, okay, is generated by, I would say, a section of k star, right, as an algebra. So, of course, if you take a degree minus 2, whatever, minus 2, these guys are sent to 0 because it's concentrated in okay, so, okay, and so yeah, here I wrote all this consequence of the derivation condition is that if you want to pass from one side to the other side, you're constantly using this derivation condition. A bit the way I did it here, quickly to prove that there are no higher terms. Okay. And let me look at, because I have notes also. Okay. Okay. And it's all, how much time? 20, okay. So just to sum it up, what's the moral, the first part of the story is that your representation of the homotopy is this DGA omega m acts for representation of the homotopy. They act on the graded vector bundle, and now they act for actions of the homotopy that are extensions. You are acting on this graded algebra. Okay. That's why. So somehow you can think of extension as the natural notion of actions of the homotopy if you really want to remain with Lie algebroids, and not go out into an infinity stuff. Okay. So now, okay. What I want to explain is more the integration procedure. So the idea is that, so I mean, we have this equation, we have these operators that translate, that encode the extension, but I mean, they're pretty much algebraic. I don't see them, it's not so clear what they do geometrically, like with pictures. And even with, for when you pass from the algebroid to the groupoid, it's always a bit more geometric to work with the groupoid because, for me a group is more concrete than the algebra. Okay, so recall now that if I take an extension and I split all my extensions, and I have one form by using derivation of k. The symbol is projectable. Well, there's a few details that I'm hiding here. Okay, and what this integration procedure yields is what is called a strict two-functor that is holonomy. Okay, so what I want to explain, if I manage to do it, is what is a strict two-functor and why is this geometry more geometric than it looks? Okay, because it seems like I'm getting even more algebraic, but this is false. Okay. So here, maybe I'm gonna write this here. So first, let me check. Okay. So categories. So I may say category and then I think of groupoid, but what I say makes sense for categories. So so what is a functor? What is a groupoid? I want to explain quickly what is a groupoid, the two groupoid, the functor, two functor. Okay. So in a groupoid, basically what you have are you have two things. You have objects and you have so say X, and then you have morphisms. Okay, so the morphism, you see them as arrows between objects. Okay. Now, if I put a 2 in here, a 2 groupoid, it's just adding one extra layer of things. So now you have 2 morphisms. And these 2 morphisms are, in fact, so these morphisms, they are morphism between objects. The 2 morphisms, the extra layer that you add up is you should think of them as arrows between morphisms. So the extra thing you're adding up is now, I have an arrow A0, an arrow E1, and I'm putting an extra arrow here. Okay, so X, Y, and I'm gonna call this sigma. Okay, so just think of a usual groupoid, and you just add up this extra layer of morphism between morphisms. Of course, you can compose morphisms. You can compose 2 morphisms. As it happens, you can compose them horizontally, vertically, but for now, let me say this: those are strict. Okay, so. Sorry, no. Okay, so that's a true groupoid. Okay, now if you have a groupoid now and another groupoid, and I take a functor f. Okay, so what is a functor? It means that I need to put it like this. Is that you take objects to objects. Morphisms to morphisms. And the picture is that if you have an arrow from x to y, your functor will spit out an arrow from f to x, and this is f of y. Okay, so that's a usual functor between two groupoids or two categories. But so you go from here to here to here to here. Okay. Now, what happens? What is a two functor? For a two groupoid, you have one extra layer. So I'm going to put a two groupoid, a two in here. So now I have an extra layer of two morphisms. So I'm going to send two morphisms to two morphisms, right? Okay, and sorry, I put a f at morphism. So the two morphism, remember that it goes from A0 to A1. And guess what? Here you have going to have A1, f of A0. And now your two functor, you're going to have an f of sigma. Okay, so it's just putting one extra layer and making everything commute. Of course, as a two functor, it should commute with a product and all the structure involved. Right. Now, what is this? First, what is this strict two functor in our case, and why do I call it a strict functor of holonomy? So in that case, I'm interested in, okay, it goes from P2 of AM. So P2 of AM has objects M. These are AM path. Actually, you should take V homotopy classes of A path, but just think of A path. And these are A homotopies. Okay, so now that's my P2 of AM. Okay, so you can this is what we call the Weinstein 2 groupoid. Okay, because if you have just object morphism, essentially you have the Weinstein if you mod out by homotopies. But here I'm taking A path homotopies between them. Actually, I'm modding out higher homotopies, so homotopy between A homotopies between A homotopies. But let's forget about this. Okay, and my functor, so now it's called holonomy. And actually, it's landed into two groupoids. So objects are groupoids. Morphisms are, functors. And two morphisms are natural transformation. Okay. And so what this business says is that, okay, if I take a path in the base, so I'm taking a path in the base, I can look at the kernel in the fiber over this guy. So first I'm taking a point, I'm taking a point X, okay? And I could associate a groupoid to this point, okay? That's the first layer of my functor. What would be this functor, this groupoid, I will just integrate the kernel of the restriction of the kernel above it. Okay? If it's not integrable, you take topological groupoid. It doesn't really matter. I mean, this is more formal, to be honest. Now, if I take y, of course, I have another groupoid, sorry, which is the restriction at the fiber over it. Okay? But now, if I take a path between these two guys, I can use this covariant derivative that is related with the connection in order to induce some holonomy. Okay, so that would be the holonomy along A0. And because this dA takes values in derivation of the kernel, the holonomy is a Lie algebroid morphism. So when I make the integration on both sides, it integrates to Lie groupoid, if it's Lie, but it integrates to groupoid morphism. Okay. So, okay.
Sorry to interrupt, but here I struggle to understand the right side. When isn't it two categories of groupoids? I mean, for each
No,
we are going to give one groupoid.
What?
No, for instance.
Yes, yes.
K or
Yes, two groupoids, object, our groupoid, morphism, functors, and natural transformation.
yeah, and you call it two groupoids.
I call it two groupoids. No? Okay, well, or two
Group, that's okay.
The two categories, yeah.
It's not a matter of name.
Right. Well, some called two cats, right, for the two category of categories, right, or cat also. Yeah, but I agree. I actually agree with you. I agree that it's confusing to put some twos everywhere. Okay, so now, so that's the first layers. But what happens is that there's curvature. This is omega that is messing around. If there was no curvature, this is the general principle is that if you have two homotopic paths on the base, okay, then the holonomy does not depend on the homotopy class. And as it turns out, there is curvature, but it doesn't really matter because if you have two homotopic paths on the base, you're going to have two holonomy, one holonomy along the first path, the holonomy along the second path. And now you have two functors from the restriction of the kernel to each fiber. But they turn out to be, there is a natural transformation associated. Okay, so they are different, but they are naturally isomorphic. Okay. That's what it tells you. So basically, you can think of, here you take a k path, you can send it into a k path here by the first holonomy, another k path here by the other holonomy, and the disintegration procedure says you have natural transformation, okay, that is given, that is associated with omega by the curvature, okay? And just to make a sanity check, okay, look at what happens. So I didn't give the formulas, of course, but morally what happens is that the holonomy along an A path is the integral along A of D. Remember that, look, D is one form with values in derivation. Okay? And the holonomy along sigma is the integral over a two form, okay, along a superficie. Sigma is a homotopy. Okay? So it makes a lot of sense, right, to integrate one form along a path and the two form along the homotopes. Okay? In fact, when you think of it, this is some kind of non-abelian Stokes theorem. In a very basic example, you recover exactly the Stokes theorem, because here, when instead of having a homotopy, here you could say A is partial sigma and integral over partial A. Now, omega here would be some D of alpha, and of omega equals of A, sorry, A of alpha minus A1. Okay, something like this. Sorry, I'm gonna. of omega. Okay. So you can write that the integral over omega is this difference, okay? But that's because these two paths are the boundary of the homotopy, and in this kind of trivial case, it turns out that this omega is exact, okay? But I think it's a good idea to think of it as a non-abelian Stokes theorem. Now, and I have 10 minutes, 5. Okay, so what is the integration procedure for morphism? Okay, now I want to give an idea of not only you can integrate these rather bad things, but it's functorial in a certain sense. Okay, and I think it's beautiful. It's beautiful when you think of it. Okay, so now I'm taking a morphism of extensions, and I'm going to split both extensions. Okay, now remember that out of it I have two functors. Okay, of holonomy, the guys I explained here. So I have one of these guys and another one associated to the other extension. Okay? Now, the phi, okay, because I'm splitting AE and A prime E, I can also, I can split the phi, right? So I'm taking phi to be, so I split this guy, I split this guy, and now I have a map. So what this phi becomes is a map from the pullback plus K to the pullback plus K prime. Okay? To simplify, I'm assuming that they're over the same base. And the general thing is here is that, oh, it has to commute, so AM is sent to AM, and this K is sent to, there's a map from the kernel to the kernel of the other prime, which is just the restriction in the end. But there's an extra term here where theta is this one form on A with values in a section of phi star K. Okay, and what this tells you is that, you know, here geometrically is that I'm splitting in here and a splitting in here. When you take a general morphism, it will not send the horizontal space to the horizontal space, right? So you have one horizontal space and here, and this one might be sent to another one. So you have to correct somehow this the failure of respecting this horizontal space, and that's exactly what this theta k measures. So let me summarize again. You have the algebroid morphism between extensions over the same base. You split both sides. You split also the algebroid. And the integration procedure now what gives you a two natural transformation. Okay. So just to be short, you see that's a functor. Okay? A natural transformation goes from object to morphism. So that's what a natural transformation. When you add up this extra layer, you can send morphism to two morphisms. Okay? So that's the idea. So now when I have a phi, the idea is the following, that now I'm taking to each object x, okay? Now I have two kernel. I have gk, the restriction over x, so gkx, gk prime x, okay? And what I'm associating is a morphism. These morphisms go from the fiber to the fiber, okay? So this part is just the restriction of phi. I have the restriction of phi to the kernel, and I can integrate everyone. Okay? So that's the first part here. To an object, I associate a morphism. Now, on this side, morphisms are A paths. So now I'm taking just one A path that goes from X to Y. Okay? And I should associate the two morphisms. So what happens here is you have one A path only now, and the holonomy in your first along this path in AE. But you have another holonomy which is in A prime, okay? So that goes to G K prime to G K prime X, G K prime X, okay? And of course, you know, if the horizontal bundle were respected, if this theta was 0, this diagram would commute. Okay, just think of you choose two harassment connections, submersion, and a map that's nice enough to respect both. Yeah, but so what this tells you that, oh no, in general you want to keep this theta because you in general you don't even know if you can correct things. So the idea is that now if you compose these things, this is a functor, this is a functor, a functor, a functor. So now this commutes up to a natural transformation. Okay. So basically this would be the integral over theta, and everything is nice enough. Okay. So let me just finish that it works kind of nicely. For instance, we could replace the base, okay, and also think of even from GK, you know, like these maps could be empty. I mean, not in that case because I put back everything. But I'm saying from the one fiber to another fiber, it could be just, you could send all the fiber to one point, okay? And something completely different happen. I mean, it works nicely, really nicely. And as you can see, it's more geometric than it looks when it's written this way. I think, yeah.